let's talk about simplifying rational exponents. And we're going to do that by finding a pattern, which is so nice. I love to find patterns. You know, our brains just try to find patterns all the time. We're wired to do it. It's what we want to do. So let's have a good time finding some patterns about rational exponents. Sound good to me. Cool. What is a rational exponent? What's anything that's rational? Something that can be expressed as a fraction, right? Expressed as a fraction. As opposed to irrational things that can't be expressed as fractions. But right now we're just talking about rational exponents. Things that can be expressed as a fraction, or, where does that name come from? Or a ratio, right? It's got ratio in there. And a ratio can be written as a fraction. Ta-da! Cool. All right, so we have the square root of 2 is equal to 2 to the 1/2. Well, I know the index here is 2. So I wonder maybe if that 2 went here, but I'm not really sure where that 1 came from. Let's move on, see if we can figure it out. The square root of 3, again, that means there's a 2 as our index. I don't know where that 1 came from. I don't know, let's keep going. Okay, this says the cube root of 4 squared is equal to 4 to the 2/3. Oh, interesting. All right, so I see that index went there, and that exponent on the inside of the radical became the numerator of the fractional exponent. So wait, let's back up. Does that make sense with our other 2? That very first one, the square root of 2, said it was equal to 2 to the 1/2. And we're saying now that the exponent of the radicand, that vocab word, exponent of the radicand becomes the numerator of the fractional exponent. Well, the exponent of this radicand, this 2, is 1. So that does make sense. The exponent of this 3 is also 1, so it does make sense. Guys, this totally makes sense. We found the pattern. This is great. Cool. So this 5th root of 6 cubed is equal to, right, that 3 went here, and our index is going to become the denominator of this fractional exponent. The 5th root of 6 cubed is 6 to the 3/5. Wild. So wild. How about the third root, cube root of 2 to the 4th? Well, I know now, using my pattern recognition skills, that the index is going to become the denominator, and the exponent on the radicand becomes the numerator of this fractional exponent. So this is 2 to the 4/3. Interesting. Y finalmente, no, not finalmente, there's a bunch left. What am I talking about? And finally. Goofy. All right, now we have the xth root, meaning we could put any number in here. Just a general expression. The xth root of b to the end. To the n. Okay, so x is our index. X is going to become the denominator of the fractional exponent. That n will be the numerator of the fractional exponent. And this b will be the base. So the xth root of b to the n is the same as b to the n over x. Cool. Oh man, can we go backwards? I think we can. I think we can do it. This says 3 to the 1/4 is the same as the 4th root. Got it, because we know that number came from the denominator of the exponents. Let's use our example back up here. Right, that was b to the n. That became b to the n over x. So this is going to be 3 to the 1/4. That means the 3 is going to be the radicand, and the 1 is going to be the exponent to the radicand. We're a bunch of geniuses up in here. Bunch of geniuses. Great. You know what? I don't want to spoil all the fun for you. So I'm going to let you do these 3 yourself, because you should also get to have a good time finding these patterns using your knowledge. I do want to do these next 2 with you, though. So this one says the cube root of the square root of n to the, or just n. Let me say that one more time. The cube root of the square root of n. So this is going to equal, we're going to go from the inside to the outside. Dun, da, da, da. The square root of n, we know, is n to the 1/2. So that's our base, right? That's our base. What's the exponent on this inside thing? Well, nothing's written, so I assume it's a 1, which means that number is going to go here. And my index is going to become the denominator. Boom shakalaka. And then, using our exponent rules, thinking way back, we have a number to a power. Our rule here is that we multiply the exponents. So that's n to the a times b. So let's do that here. What's 1/2 times 1/3? 1/2 times 1/3. We multiply straight across. So we get a 1 on the top and a 6 on the bottom. Which means our fraction here, n to the 1/2 to the 1/3, is really n to the 1/6. Cool. And finally, this one's just the most fun. It's just a good time. We have the love root of dog to the puppy. Dog to the puppy. Okay. Using our examples over here, we know that dog's going to be our base. And puppy is going to be our numerator. And love's going to be our denominator. Oh, so cute. We got a puppy love. It's so good, yeah. All right, so let's put together, synthesize the information we gleaned from our pattern recognition, rewriting a rational exponent in radical notation and vice versa. So here's our rule. B P over Q is equal to the qth root, that's a funny phrase, the qth root of B to the P, which is also equal to the qth root of B, all of that to the P, where B is our base and P is our exponent and Q is our index. Yay! Ooh, it's so fancy. It's so fancy, 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 fancy. Great. So b to the p over q is equal to the qth root of b to the p, which is also equal to the qth root of b, all of that to the p. Totally true. All right, this this part might be a little confusing, so let's put an example here. Let's say I had the fourth root of 2 to the 5th. If I wrote this as a rational exponent, this would become 2 to the 5/4. If I had it the other way around, for the fourth root of 2, all of that to the 5th. Okay, so this would be, our inside part would be 2 to the 1/4, remember, because our exponent really here is really 1. All of that to the 5th. And then using our multiplication rules for exponents that we talked about up here, if we have something to an exponent, we multiply those exponents together. So we're going to multiply 1/4 times 5 to the 1/4 times 5. I can make that 5 over 1. Multiply straight across. We get 2 to the 5 over 4. Got it. Yeah, they're the same. Cool. So your exponent can be on the outside or it can be underneath your radical as part of your radicand. Great. You guys are doing so good. Let's keep on cruising on, shall we? Doing some examples while I get my paper straight. Do. I just want to move the paper all over the place. Come on, buddy. Come on, buddy. Come on, buddy. All right. We are going to rewrite some expressions in radical form, meaning we should have a root symbol. Right? Radical means we're going to have a root symbol. And some type of index. Might be a square root, might be a cube root, might be a billionth root. You know, who knows? Who knows what is in store for the future? Okay, we started off easy. 3n to the 1/3. What's our base here? 3n. What's our what's our exponent going to be? That was the top number, right? That's the p, that's 1. And what's our index? That's our q, that's our 3. Super simple, using the rule that we just talked about, which was b to the p over q equals the qth root of b to the p. Great. So this is going to become the cube root of 3n to the 1. If it's to the 1 to the first power, do I have to write it? Nah, we good. That's it, my dears. That is it. All right, b. 5e to the negative 4/5. Oh, heavens, what do I do when I have a negative exponent? By Jove, you're right. We're going to put it in the denominator. So this is going to become 1 over 5v to the positive 4/5. There you go. There you go. Let's keep evaluating as we have been. We'll have 1 over some stuff. So our b is 5v. Our p, our exponent, is going to be 4, and our q, the index, is going to be 5. So we're going to have 1 over the 5th root of 5v to the 4th. And we can go ahead and distribute our exponent here. So this will be 1 over the 5th root of, what's 5 to the 4th? 5 times 5 times 5 times 5. 5 times 5 is 25. 5 times 5 is 25. 25 times 25 is 625. 625 v to the 4th. Oh yeah, that's pretty. That is pretty. And example C. 6xy to the 1.5. What? I need it to be written as a fraction. Can we write 1.5 as a fraction? Yeah, for sure. For sure we can. This is 6xy to the 2/3, which means our base here is 6xy. Our exponent p is 2. Our index q is 3. So this shall become the cube root of 6xy squared, which becomes the cube root of 6 squared, x squared, y squared. 6 squared is 36, x squared is x squared, and y squared is y squared. That's it, my loves. That's it. That's how you do the thing. Using our little conversion sitch. All right, you're going to do example 2s, which mean you're going to go backwards. You're taking all these, and it will be written in exponential form, meaning you'll have an exponent. So you're going from q root of b to the p to b to the p over q. So your answer should look like this. Fabulous. So again, you guys are doing all of these for me. Your big fat scholar brains. And then on the very back, the very, very, very back. Let's go. Ready? We're gonna put it all together. Simplify expressions that contain rational exponents. Yeah. So do all of the things that you know how to do together. I'm going to show you example number 6. Example number 6, meaning you're going to get the joy and pleasure doing example 3, 4, and 5. I'll show you example number 6. Okay. So we have a lot of fun things going on here. We have 8a to the 12th over 27b to the 9th, all to the 2/3. So let's give everybody that 2/3 exponent first. So this is going to be 8 to the 2/3 times a, well, let's just do that real quick. A to the 12 times 2 over 3. I can do a little cancellation. Oh, so that's only a to the 8th. Great. Over 27 to the 2/3. Yeah, let's do the same thing here. B to the 9th to the 2/3 means I multiply those together. That's over 1. Crossy crossy, cancel cancel. So that's really b to the 6th. Okay. Now we know that 8 to the 2/3, 8 to the 2/3 is the same as the cube root of 8 squared is the same as the cube root of 8, all of that squared. I'm going to use this one here because I actually already know what the cube root of 8 is. And you shall soon have that mesmerized. But let's just do the cube root of 8 and then we will square our answer. So the cube root of 8 means we're going to break down our 8 into its prime factorization, meaning 4 times 2 and 2 times 2. It's the cube root, so we need a group of 3 things that are the same, which is all that dude here. So the cube root of 8 is 2. So now the cube root of 8, which is 2 squared, right? Squared is going to be equal to 4. So that means that 4 is going to go in place for 8 to the 2/3. 4a to the 8. Hanging in there. We took the cube root of 8, which we found was 2, and we squared it, and we got 4. Awesome. Now let's tackle this denominator, shall we? I think we shall. You know, I think we really shall. Let's do the exact same thing with 27 to the 2/3. We know that that is the same as the cube root of 27 squared, which is the same thing as the cube root of 27, all of that squared. Again, I'm going to use that last one because I know what the cube root of 27 is, and so shall you. The cube root of 27, if we break that down, we get 9 and 3 and 3 and 3, which means we got a group of 3 threes. So the cube root of 27 is 3. Now let's square that, because that's what we really had here. We squared it. 3 squared is 9. And that 9 is going to go in for where we had 27 to the 2/3. 27 to the 2/3 on the bottom. Over b to the 6th. Can't reduce that at all. So that's our answer. Ah, that's pleasant. That's really quite nice. All right, scholars. That's it. Keep on that hustle. Keep on that good work. I love you. I'll see you next time.